Okay, you're not doing grade 9. AP Chem. There we are. All right.
I wish I was in grade 9.
Right? Let's name these compounds. Let's write a formula or two. 99.
I have some questions.
A 0.1 molar solution of ammonia is titrated with HNO3, which is a strong acid. They're both the same concentration. Which of these statements is most likely true? You have A. What the heck happened there? It just disappeared on me. That's great. We have a strong acid and we have a weak base. So will the pH of that titration at the equivalence point be 7, greater than 7, or less than 7? You should be able to tell me this right away. Less than 7. Yes? Because this is a multiple choice question, you can be like, strong acid beats weak base is acidic. Okay? Terrible explanation, never write that, but for multiple choice it works really well. And so you can be like, it is 5.28, and therefore methyl red can be used as an indicator. You don't even have to look at the indicator because it has to be 5.28 because that's the only one that's below 7. Yes? Now, why is it actually below 7? Because when you put NH3, what happened? Oh, there we go. When you put NH3 with HNO3, who are the products? NH4 plus and NO3 minus. So which one of those two things makes the solution acidic? NH4 plus. So NH4 plus will do what? Hydrolyze. And you will end up getting NH3 plus H3O plus, and it is that hydronium that makes it acidic at the equivalence point. Any other questions? Yes, Demi. 92 and 93, perfect. 92 and 93. Carbon dioxide gas in the atmosphere dissolves in normal rainwater. This causes normal rainwater to now. What is CO2? CO2 is what kind of an element is carbon? Non-metal. And oxygen means that it is an oxide. So we have a non-metal oxide. What happens with non-metal oxides when we put them in water? They're acidic. Could you please write the equation for what happens when you put CO2 in water? What do we get? Do you remember what you do? You smush them together. Who goes first? H. How many H's do you have? 2. And then who comes next? C. And how many O's do we have left? 3. O3. So we have made carbonic acid, and that can then, of course, form H plus and HCO3 minus. And so it will not be slightly basic. It will not be unaffected and remain neutral. It will be hydrogen ion concentration will be slightly greater. Well, that's wrong. The answer is D. That would make sense then why you're like, hey, hang on, fix key. Fix key. D. Okay. And 93, let's find out if this is another one that I've messed up on. We have C2O4, NH3, and PO4 from weakest to strongest. This one we need our data table. And we have C2O4 is here. NH3 is here. What was the third one? PO43 minus? Okay, so that is our strongest base, so it should go PO4 is stronger than NH3 is stronger than C2O4. Does that make sense? So let's see if that was actually what was there. Okay. So it should be A. You look unhappy, Amy. You looked unhappy for a moment. Okay, okay. All good. Oh, from weakest to strongest. Well, but the symbols are from strongest to weakest. Okay, so I just need to fix this question. Was the answer A? It's B?
Yeah.
Okay, so all my little greater than signs are all wrong. So I need to fix and change them all to la la, 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 like that.
Wait, so
PO43 minus is the strongest because it's at the bottom of the table. So here's the problem. On the question, I wrote the greater than symbols the wrong way. Yes? So if we fix those symbols, then it will match with what it says in the question and what the answer key says. Is good? Okay. Tony, you okay? Okay, cool. All right, what's next? Amy. 47 and 106. Sorry, she had her hand up before. You're like, you're just ignoring me. No, she had her hand up and I went to Demi, and so I'm going to her next. So 47 and then we'll do 106. Yeah. I'm not ignoring you, Dorothy, I promise. I promise. Oh, didn't we do this one yesterday? Okay. That would make sense. So number 47, we have a diprotic acid. So that's like H2A. Okay, and it reacts with 2NaOH to give Na2A and 2H2O. It requires 4.5 times 10 to the minus 3 moles of NaOH to react. So the moles of NaOH are 4.5 times 10 to the minus 3. Which means the moles of HA, because it has a coefficient of 1, will be half of that. Yes? And half of that gives us the value 2.25 times 10 to the minus 3 moles of H2A. Molar mass, then, we're going to take our 0.45 grams and divide by the moles of that acid, and we get 200 grams. Is good? Okay. Dorothy, you wanted 106? Okay, cool. Sorry. (106). Which of the following combinations is best for preparing a buffer that works in basic conditions? So what we have here is we have a weak acid and the salt of its conjugate base. Yes. We have a weak base and the salt of its conjugate acid. What's the difference? Oh. Okay. Here we have a weak base and we have a strong base. Yes. And over on the right, we have a weak acid and the salt of its conjugate base. Which of those is going to form a basic buffer? The weak base and the salt of its conjugate acid. Once we're done this today, I'll actually go into like showing you some calculations in AP. Like this is like a regular Chem 12 kind of answer. Okay. So if you want basic, use a weak base and the salt of its conjugate acid. If you want an acidic buffer, use a weak acid and the salt of its conjugate base. And that'll get you through Monday's test. Okay? But today we're going to learn more because that is an unsatisfactory answer. It's kind of like, but why? Okay? Yeah. Anything else? Anyone?
We do 46.
46 and then 58. 46 and 58. What volume of eight? Whoa. What? Where is it? So irritating. It jumps all over on me. 46. There we are. What volume of 4.0 times 10 to the negative 2? So that is 0.04 molar HCl. How many liters is needed to neutralize 2 times 10 to the negative 1, so 0.2 liters of 0.01 molar LiOH. So here, that will give me 0.002 moles. Yes, is that correct? Do you guys agree? Yes? Okay, so I need some amount of liters times 0.4 molar to give me 0.002 moles. So I'm going to take 0.002 and divide by 0.04 and hope that works. 0.002 divided by 0.04 equals 0.05. Okay, and so that would be A. Yes? Cool. And we wanted 58. In comparison with a strong acid, weak base, titration, the equivalence point of a strong acid, strong base, titration. So this one would give you the equivalence point. What would the pH be like? It would be less than 7. And for strong acid, strong base, the pH at the equivalence point would be 7. So in comparison, this one occurs at a higher pH. A. Yes? Okay. And so you can just ignore the rest of the answers. Anything else? 55 and 52? Okay, 55 and 49. Okay, so 55. Didn't we do this yesterday? We did. So what we have is we have a buffer solution because we've got a weak acid and we have its conjugate weak base, and they are both at, if we say we've got 1 liter, then we have 1 mole of this and 1 mole of that. So that means we have lots of weak base and we have lots of CH3COO, and we add 0.2 moles, which is significant compared to 1 mole, but not obviously going to overwhelm 1 mole. So the pH is going to rise. So it has to be either B or C. Which one seems like a more reasonable increase given that we have now reacted 20% of the acid? I would think it would be that one. Yes? Yeah, because the other one is just such a small, an 0.01 change, that's so small. Okay, yeah. And we wanted 48. Was it? You're good? Okay.
Oh, and we do 61.
61. Okay, we have several indicators to determine the pH of a solution, and we obtain the following data. Okay, so we would need our book for this. I'm not going to flip back and forth. I'll just write some stuff down. Thymol blue is yellow, which means our pH is greater than 2.8. But I remember that thymol blue is funny. It's got 2 transition points. So it turns from yellow to blue, pH 8. So it is less than 2.8, or sorry, greater than 2.8, but also less than 8. Methyl orange is yellow, which means it's greater than 4.4. So it's not this one. It's not this one. It's greater than 4.4. I don't even need to look at these. It'll be this. The answer key says what?
The answer key says, because it said B.
Said B?
Yeah.
Oh, I guess B is greater than 4.4 because I'm a dummy. We do need to keep going. Okay, sorry. I read that wrong. All right, methyl red is red. Methyl red, 4.8 to 6.0. So it is red below 4.8. Ah, there we go. So that takes that one out of the running, and it is B. So we don't need to look at phenol red or phenolphthalein. Yeah. Is good?
Yeah.
Okay, cool. Yes. 100, sure. That's okay.
Similar to the one at 106.
That's okay. Which is the best for preparing a buffer solution that works in acidic conditions? So we are looking for a weak acid and the salt of its conjugate base. Here we have a strong acid, that's out of the running. Here we have a weak acid and the salt of its conjugate base. Boom. But let's just take a look at things. Here we have, this is a weak base and the salt of its conjugate acid. Yes. And then this one is it's amphiprotic, but I feel like it's more basic than it is acidic. That's just my guess. I would have to actually look on the chart. And it's a strong base, so.
The answer key is B.
Well, the answer key is B? Well, the answer key is wrong. It should be D. Fix key.
It's D. Oh, never mind.
Oh.
No, it's D. No, it's D. Oh.
Okay. Okay, so it's all right. Yes. 62. A substance has a Ka of 4 times 10 to the negative 12. From this information, it can be concluded that the substance is A. Which 2 things can you eliminate immediately? In fact, there's 3 things you can eliminate immediately. You can eliminate anything that is strong, and you can eliminate anything that is a base. Only weak acids have Kas. Yeah? Weak bases do not have Kas, they have Kbs.
Because they might not.
What?
So like, is it because they might not be able to control it?
Well, no, the question says it has a Ka.
Also,
So you can conclude from that that it is an acid. Okay? Because it says, what can you conclude from that? Yeah? So you know it's an acid. You know nothing about its status as a base, but from that you know it is an acid. Yeah? Cool, cool. Shall we move on? I can answer questions tomorrow as well. Yes? Okay, excellent. Good stuff. We're going to finish acid rain today. No, we got close, but we didn't quite finish it. We got to page 117.
Oh, yeah. Girl.
This is page 117. You know what happens when you learn something in the last couple days before a test? Everyone says, oh, it's not important. Right?
Yeah.
Uh-huh. I've just put 2 stars beside this to say, even though we're learning it, it's like one of the last things we're learning in this unit that could be on the test. It is still important. Okay? And people think, oh, I don't actually need to know that. Why would I need to know that the sulfur comes from burning fuel like coal? You do need to know that. It is part of the curriculum. Okay? Why would I need to know that car exhaust gives off nitrous oxides? Because it's part of the curriculum. Yes? Yes. Pardon me?
we need to know like why.
You need to know why. So let's take a look. That's what we're looking at. We're looking at why. When burning coal or other fuels, and if you remember, we had our little picture of coal, which is mostly carbon, but we have some sulfur impurities. So S reacts with O2 to form SO2. That seems fairly straightforward, yes? Could you remember that if you had to? Yes. So this is an acidic, what's the word we call it? An acidic anhydride, yes. Now, in the atmosphere, we get further oxidation. Oxidation means sticking oxygens on, or at least that's one meaning of the word oxidation. We'll learn another one soon. Okay, sticking oxygens on, producing sulfur trioxide. Okay, could we balance this, please? I think so, yes. Anyone have trouble balancing that? It's okay if you do. I can show you how, if you would like. Nobody needs help? Okay, thank you, because I'm sure there's other people who are just like, no, I don't want to say it. I don't want to say it. It's complicated because you've got an odd number over here, yes? And you've got an even number over here, but it's in 2 different places, right? So that's icky, yes? how I would deal with this is I would use halves. I would put in a half O2 because that would give me 2 oxygens plus another half of an O2 gives me 3 oxygens, right? A half of an O2 is 1 oxygen. So now I have 2 plus 1 is 3. Now it is balanced, and I would just need to multiply everything by 2. So that would give me coefficients of 2, 1, 2. You can also just do it by hacking it out, you know what I mean? Like just brute force it until you get it. Everything's going to be small numbers, but I like that because I don't have to worry about it too much. So now we have 2 acidic anhydrides. Sulfur dioxide and sulfur trioxide. So we have SO2 and SO3. Those are our 2 acidic anhydrides, there and there. And they do not react with oxygen. Nope, they do not. What do they react with? They react with water. Sorry, what were you going to say? No, it's not.
Rainwater has a pH of 5.6. So
Yes. Yes.
So in theory, it's like it tastes more solid than water.
Maybe. I don't know. Maybe.
I think that.
So what? But like that works for tap water as well. I mean, anything that's been exposed to the atmosphere for any amount of time. And when you run the tap, like it's being exposed to the atmosphere, right? It's bubbling, you know, whatever. So there's always going to be absorption of CO2. Okay, so tap water is slightly acidic.
So then, technically, pH 7 water is
pH 7 water, it is possible. You have to distill it and you have to deionize it and then you have to seal it off from any source of carbon dioxide. So if you distill it and then get it isolated, pH 7.
then what can we use that?
Technically, yes. In reality,
Why do you think pressure?
because we don't, since we've lost our lab aid, we do not use our water distiller, and so we just use tap water. Yeah. Okay, so this should not be O2, it should be H2O, and this should be H2O. Okay, and that should be a liquid, and that should be a liquid. Fix. So we end up with, and again, you just cram them all together, you end up with H2SO3, sulfurous acid, and H2SO4, sulfuric acid. Which one do you think is the bigger problem? Sulfuric acid, because it is strong. Okay? So this is the bigger problem. Not that H2SO3 is a small problem, because it is actually a relatively strong weak acid. So this is a problem, and this is a bigger problem. Okay? Problem, bigger problem. And now we're going to move on to nitrogen. Where does nitrous oxides come from? They come from cars, okay? So we have a little car. So we have NO2. Okay, now you do not need to know these reactions. These reactions are like, there's too much. Yes? But you should know that it is NO2 that does it. But what you do get is you get N2 plus O2 gives NO. And then there's more oxygen around and the thing is still burning. So you get NO plus O2 gives NO2. You also get N2 plus O2 just gives you NO2. So both ways you end up with NO2. Yes? And NO2, regardless of how you get it, NO2 is an acidic anhydride. It is a non-metal oxide. And nitrogen dioxide reacts with rainwater. And again, you're going to get, this is one of the weird ones. You get HNO2 and you get HNO3. You get a weak acid and a strong acid. Do you need to memorize this? No. Should you know that NO2 can eventually, like the nitrogen from the car engine, can eventually give you nitric acid, a strong acid? Yes. Because that's why it is in, because this is a problem. But this one, because it is strong, is a bigger problem. So these are human sources of acid rain. Burning fuel, burning coal, and car exhaust. Natural sources of acid rain, volcanoes produce SO2, and you can get then, what acids do you get from SO2? Sulfuric and sulfurous. Okay, so you get H2SO3 and H2SO4. And lightning can actually cause the nitrogen and the oxygen in the air to produce NO2, which means you're going to get nitrous and nitric. Some areas have a natural protection from acid rain. And that's because the rocks and soils contain carbonates. What kind of a substance is carbonate? It's a base. Yes? Where'd you go? There you are. So carbonate is a weak base, so natural protection. Rocks and soils have carbonate. CO3 acts as a weak base and it neutralizes the acid. Could you write the equation for this? And once you have H2CO3, what can it become? H2O and CO2. Whoops, that should be a big O. Yes.
With C's? Oh yeah, never mind. You answered the question.
Yeah. So sometimes if you have an area where there's been a lot of acid rain, they will actually dump some limestone in there. Limestone is calcium carbonate. But this process is expensive. Yes?
I don't know if it's that.
Oh, I don't know that it matters. No. Is calcium sulfate solid? Could be. I don't know. Doesn't matter. Yeah. Problems associated with acid rain. Aquatic life can die
What?
or be
Really?
affected. Yes. If it gets too bad, yeah, absolutely. Forests can be weakened and killed. Now, we don't hear as much about acid rain these days as we used to because most coal burning plants now have, do they call them, they have devices to remove SO3 scrubbers on smokestacks.
There's scrubs.
Scrubbers? I don't know. They're like a chemical thing. Let's see. It says SO3 plus. They involve calcium oxide. And so above the smokestack, probably what you'd have, right? Here's the smokestack. And then somewhere in the smokestack, they would have some CaO. And they'd have like, layers of it or whatever. And in order for the smoke to get out, it would have to pass through the CaO. Yes? And when it passes through the CaO, as long as it's hot enough, and I assume they would like have heaters or whatever, it forms calcium sulfate, which is a solid at that point. Yes? And then the calcium sulfate is removed by electrostatic precipitation. Yay. Okay? So forests are weakened and killed. Minerals are leached out of the topsoil. Aluminum ions are released, which are toxic to fish and plants. Metal and stone buildings and statues, especially marble, calcium carbonate, are damaged. And finally, acid rain is carried over large distances due to high smokestacks. So, problems, possible solutions, international conferences and agreements to limit sulfur in fuels, and NO exhaust in cars. Using less polluting energy sources. So instead of using coal, you might use solar or wind or geothermal or hydro. Yes? Industrial processes being modernized. So pulp mills use hydrogen peroxide instead of sulfites. And there is recycling, and in cars, catalytic converters. Limit the amount of NO2 produced. You should be able to come up with a harm from acid rain. But that shouldn't be too difficult. You can be like, oh, what happens? Bad for things in lakes, aquatic life. Bad for forests. Yes? And if you've got two, you've probably got that covered. Okay? And that's it. So that is regular acid base part 2. And now, you are going to come and grab one of these. What about signing up to these? So they can just for acid base and what to
Okay, give you one.
You may have 3 books for a very short period of time. You weren't supposed to. You were supposed to be done with that one on Friday, but now it's till Monday. So for the weekend, you will have 3 books. There's AP extras. AP extras.
I don't think it's ever been. What do you want? Wait, why do I have 3?
Because it's so skinny, you're not used to picking up such a light thing. Yeah.
Oh, wait, that's the point. I got like people on side.
What? Which one?
Stop. Yeah. Stop. Get away.
I remember seeing.
This is your answer.
Yeah.
Mine?
Okay, we're gonna slam through this really quickly. And the reason we're slamming through it really quickly is that I'm gonna show you the hard way and then I'm gonna show you the easy way. Okay? It's not actually hard, it's just time consuming. Yes? Okay? So if you want to calculate the pH of a buffer solution, you have an equilibrium, yes? And you have an equilibrium of a weak acid and its conjugate, weak base. Together, those make a buffer. This is page 1, okay? Page 1. Do they actually have to exactly equal each other? No, and we'll get into the subtleties of that later, but in this case, they do, all right? And because we have both of these things, we can show the equilibrium between them. We can show acetic acid in equilibrium with CH3COO minus and H plus. If you wanted to have water in there and have it be H3O plus instead, that would also be perfectly fine. Yes? Sorry? Not all equilibria are buffers. It needs to be a weak acid and its conjugate base. Okay? And in order to be a buffer, you need to have a decently high concentration of both. Okay, so you couldn't just have the acid and, you know, whatever base it happens to form, because that's not enough to buffer it to shift the other way. Yeah? 0.5 is good enough. You'll be able to tell. Do you know what I mean? From the question, it'll either say this is a buffer solution, or it'll give you some choices, and you'll be like, I'm going to pick the big one. You know what I mean? So yeah, don't fret about it too much. It'll be obvious. Okay, and if it's like, you know, if you've got something like 0.0001, you can be like, oh, that looks small. That looks like probably not enough. Okay. All right, so we have 0.5 and 0.5 of those guys, and those are our initial concentrations. That means when we stick those in right at that moment, the hydrogen concentration is 0, which means that the going up has to happen on the products, and the going down has to happen in the reactants. So we end up with 0.5 minus X, and we end up with 0.5 plus X, but those are going to give us a quadratic equation. So we will normally assume that X is insignificant. So now what we have is we have our Ka expression. We have acetate ion times hydrogen. Okay, and let's recall acetic acid is 0.5 because we got rid of the X, yes. Acetate is 0.5 because we got rid of the base, or sorry, or the X. I don't know what I'm saying. Yeah, we got rid of the X. And hydrogen is X, and we know the Ka, right? It is 1.8 times 10 to the minus 5. And so we get 0.5 times 0.5 is equal to, oh, look, those cancel out, and we're left with X is equal to Ka. Okay, Remember, this is Ka. So if you have a buffer where the two concentrations, weak acid and conjugate weak base, are equal, then the concentration of hydrogen is equal to the Ka. Does this seem familiar? Have we come across other situations like this before? Yes. Pardon me? Yeah, it's just like the indicator, and it's just like the pH at the half equivalence point, because at the half equivalence point, you are in a situation where these two concentrations are equal. Yes? So this is the same as a half equivalence point, but we're just not doing it through a titration. We're just doing it through putting the acid and its conjugate base into solution. Yes?
So are all buffers like out of like
Not all of them, because I don't have to be at 0.5 and 0.5. I could have 0.5 and 0.4, and that would still be a buffer. But what will happen is that will adjust the pH up and down a little bit, and we'll see how to calculate that. Okay? But you should know, and this is actually quite important, is that Ka, if concentration of HA is equal to concentration of A minus, then concentration H plus is equal to Ka, which also means that pH is equal to pKa. Okay. Oh, look, I wrote it down, but it's already here. If A equals A minus, you can use H plus as Ka, and pH is equal to pKa. There we go.
like so this here I think you said earlier is like negative bond. Yeah.
Yeah, to find the pH.
You have to like specify like because this is this, so we can use like negative bond.
I would say because this is true, then pH is equal to pKa. If you want a buffer at a specific pH, you can choose, we call it an equimolar mixture. What does an equimolar mixture? It means the 2 moles are equal. Equal, equi, okay? Equal, moles, equi, molar. Moles of HA is equal to moles of A minus. Also, concentration of HA is equal to the concentration of A minus. Pardon me? It is the half equivalence point, but you can also get there without doing a titration by throwing in 1 mole of your acid and 1 mole of the salt of its conjugate base.
So it's like half equivalence point is just like a specific.
It's the half equivalence point is a specific case where we get this. Okay? So if you know that you want, say, a pH of 4.74, you can be like, which of these acids has a Ka where I can take the negative log and I'll get like 4.74-ish, okay? So let's just say I wanted a pH of approximately, let's just pick a pH, any pH. 6, let's have a pH of 6. Okay, so we're going to look at this and we're going to like, okay, which of these acids would give me a pH of about 6? I would probably want maybe this one, right? Because that's sort of a largish times 10 to the negative 7.
Try.
What's that? Well, yeah, you could try it. You're not going to get pH 6, but you're going to get pH 6 point something. Yes, because it's times 10 to the negative, it's something times 10 to the negative 7. Why don't you figure out what the pH of an equimolar mixture of H2CO3 and HCO3 minus would be? I get 6.4. So I might even be like, oh, maybe I can get closer to 6.0 with that one. Let's try that one. 4.1 times 10 to the negative 7 log. That's 6.4. They're about the same, right? So not that much different from each other. So I could use either this one or this one. This one's probably cheaper, so I would probably use that. Yeah, because I think, yeah. Is good? Okay. So now, oops, no, don't want that one. I want that one. There we go. There we go. Okay. Now, if we want to use some log rules, we can broaden this equation for cases where HA does not equal A minus, okay, where they aren't exactly the same, so you can just cancel them out. So let's look at the log rules that we have. Rule number 1, log of m times n is log of n plus log of n. Yes? Log of m over n is m log of m minus log of n. And rule number 3, log of m to the k is k times log of m. Are you going to actually have to derive this? No. Okay. Let's take a look though. We're going to take our Ka expression and we are going to solve it for h. Yes? So we take Ka and we solve for h, and when we solve for h, we get h is equal to Ka times, and you notice how we have this term here that contains our weak acid and its conjugate base. Yes? Well, now, if we wanted to do the pH, we would have to take the negative log of the H, yes? And we'd have to take the negative log of Ka and the negative log of, the negative log of everything. So we're taking the negative log of everything. Okay? No, I said that we're showing how you would derive it, but you will not have to derive it. Okay? This is how we get to the Henderson-Hasselbalch equation, which is a fantastic name. I'm sorry. Henderson-Hasselbalch. Okay. So, negative log of h, using our log rules, we can say that's equal to negative log of Ka minus the log of HA over A. Here, I'll put this in brackets. Okay. And we know that the negative log of H is the pH. We know that the negative log of Ka is the pKa. And we're still subtracting the log of HA over A. Now, what can we do with that negative log of HA over A? I think, wasn't that supposed to be? Oh yeah, so what we're going to do is we're going to take the negative log of A over HA. You notice we've flipped this upside down? Whoop, whoop, woo. Yes? But it's still equal as long as we put this little negative one here. Yeah? Okay. So, if that's the case, then this becomes a plus. Because of this log rule up here. M to the K is equal to K times the log. So our negative 1 is going to come over here, and then that becomes a positive. Yeah? So the negative of a negative is a positive. So now we have pH is equal to pKa plus the log of A over HA.
Why don't we go all the way to the log? Why don't we like log A minus?
You could if you wanted to, but then you have to press the log button twice rather than just doing a division and pressing the log button once. Yes? So the ratio of the base to the acid, and you know what this spells? Aha. Okay.
Oh, God.
pH is equal to pKa. And then if the A and the HA are not equal, it's plus log of aha. Yes. Why do you flip HA and A? So that you can get this negative 1 here. So that then this can become positive. Because adding is less inconvenient than subtracting. And that's the way the formula is written. You don't have to. You could leave it like this. But that's not how anyone ever writes the Henderson-Hasselbalch equation. It's always pH equals pKa plus the log of aha. Yes?
No, I think we did.
So if you use this Henderson-Hasselbalch equation, and I mean the real answer is just because that's how they always do it. You know what I mean? That's how it's done. The College Board gives you this formula. Let's go look at our data tables. Okay, AP data equations, AP equations. Look at that. Up in equilibrium. Okay, it gives you pH is equal to pKa plus the log of aha. Yes? So that is given to you. So if you are asked to calculate the pH of a buffer, all you would need to do is you would need to find the P of its Ka, the negative log of its Ka, and then you would take the concentration of the acid, divide by the concentration of the base, and then take the log. Yes?
It's like a really great question for like, first of all, equating the data, which is a
Yes.
the acid base of the
These are conjugate, yes. And it does not tell you that. So you just need to remember that these are a conjugate pair. Okay? Now, I'm going to give you one more little extra. Because the buffer is all in one container, yes? The volume in which the A is contained is the same as the volume of the HA, yes? So you could use moles instead of molarity because the liters will cancel out. So you could use moles of A over moles of HA. It just depends on what you're given and what is more convenient. Yes?
Maybe like something.
Pardon?
Like, are we going to be asked to calculate the pH?
Of a buffer, yes.
We work like other stuff.
Possibly. I think it's unlikely, but I'm going to show you how anyway. Okay? Because for certain in university, you're going to have to do that. Okay? For that, you need a rice table. But it's just a rice table like every other rice table, right? You throw things in, you go, okay, this is where I'm at, this is where I end up.
So Miss Spence,
Yes.
you don't use rice table
In what?
in university?
Yes, you do.
But it says you don't need to show a rice table.
The College Board,
Oh.
which is the AP people, the College Board does not need you to show a rice table. They don't need you to do the calculation like this. Okay? No, I'm not saying they don't want you to. I'm saying that you can save yourself some time and do it using this equation, the Henderson-Hasselbalch equation, because that's a lot less work than showing the rice table and saying assume x is insignificant and you end up with the same value using that equation. And they're obviously okay with you using that equation because they've given it to you. Yes? Okay. So you can use the Henderson-Hasselbalch equation, or you can even just use the Ka expression and chuck everything in there and solve. Because really, you can just say, oh, I want to find H. H is equal to Ka times Ha over A. Ha-ah. Okay? So here is a buffer solution where the concentrations are not equal. We have 0.5 molar acetic acid, and we have 0.4 molar sodium acetate. Okay, so we've got our 0.4, and we've got our 0.5. If we wanted to show all of our work, the full meal deal of work, yes? Then we would say, okay, we got no hydrogen. These ones are going to go up. This one is going to go down. We are going to assume that these little x's here are insignificant. Yes? Now, if it is a buffer, you can just skip the rice table and the assumption and just start here if you want to. Ooh. Ka is equal to H times base over acid. Or you can just say H is equal to Ka times Ha over A. Yes? And then you would plug in these numbers here, 0.4 and 0.5. And so hydrogen is then equal to that, and you get your hydrogen concentration. And so pH is then equal to 4.65, which you can see is slightly smaller than pH 4.74, which was the equimolar. Yes? Is good? Okay. Or you can use the Henderson-Hasselbalch equation. pH is equal to pKa plus the log of A over HA. Aha. So you'd be like, okay, negative log of 1.8 times 10 to the minus 5 plus the log of, well, this gives you 0.8, and that gives you 4.648. This would be the pH of an equimolar buffer, where the moles of acid equal the moles of base, because that's just your pKa. Yes, and then we have this adjustment factor based on the relative concentration of the acid and the base. Okay? Huh? Don't stress, just use the formula. Okay? Now, sometimes you'll find, and I don't know why we have this mnemonic, but then I found a little sheep holding chemicals, and I was like, well, we must do this. pH equals pKa plus the log of Ba. And what is Ba? It's the base form over the acid form. So in other words, aha. Yes? So I don't know, whichever way you choose to remember it, like, because maybe in, some course somewhere it will just be nice to remember it without having to look it up. Yes? but you don't have to because it is in the book. If you know the acid form, it is easy to remember the basic form because pH is equal to pKa plus the log of Ba. POH is equal to pKa plus the log of Ab. Yes. Why does it only work for buffers? Because the concentrations of the acid and the base are relatively large, so we can ignore the change X, right? Because this would normally be B minus X and A plus X, right? But we don't have to worry about that because those are relatively large concentrations because it is a buffer. So we can just get rid of those X terms. Yeah? So it allows us to make that assumption, and which then reduces this to a very simple formula. Okay. So how about you find the pH of a buffer solution consisting of 0.035 molar NH3 and 0.05 molar NH4 using the acid form of the Henderson-Hasselbalch equation and the base form of the Henderson-Hasselbalch equation.
The base one, just subtract.
So using the base form, you're going to use this. POH equals PKB plus the log of Ab, just to try it out. It's not because it is efficient. I just want you to try it to prove you get the same thing. Okay? Off you go.
NH3.
Don't try and find a Ka for NH3. NH3 is a base. Pick your acid and find its Ka. No, the whole point of the Henderson-Hasselbalch is you don't need to do a rice table. It saves you the need of doing a rice table. Did you guys get 9.10? Excellent. Did you notice that the Ka value is 10 to the negative 10, and our pH is close to 10? Yes? Because your pH, as long as the concentrations are relatively equal, they will be close to the power of 10 of your Ka value. Okay? So you can check your answer that way. You can be like, am I way off or am I in the right neighborhood?
Would you have to include the rollers the bottom
Probably not.
certain time?
I don't think so.
So,
The 1980s. Okay.
I'm running out of room, so I'm leaving off my zeros there.
Okay. Yeah. Wait. I didn't do that with the
Wait.
Yes.
But I.
Kb is equal to Kw over Ka?
Oh.
Yes.
No, that's so real.
Yeah. So I would like you guys to do page 6. Odd numbers. I don't know. You know what? Honestly, just do sum of page 6.
I think you should decide. I will decide.
There's going to be more homework. I'll put it on Teams. Homework will be on Teams. Okay, there we go.
What is this? You'll be later. Oh, I have it. What's 20%? That's 20%.
Wait, so it just keeps.
Yes.
The Kb would be the same as the.
KW over KA?
Yeah, because, I mean, in this case, it's KB for NH3, right?
Sorry?
KB for NH3.
Yes.
So then it's just 1 over the KA.
1 times 10 to the negative 14 over KA, yes. Okay. Hi, Ken.
No, you don't need to know this, but this is going to be funny.
Okay.
These are all the notes for this chapter.
It's a big chapter, right?
Oh, wait, these are half of them. I
Yeah.
have more pages.
This is a crazy chapter. See you later. And
it's only regular
actually,
chemistry.
pardon me?
It's only regular chemistry. It's not even the AP part.
I know, right? But yeah. Yes.
It's place and loss.
Yeah.
Like a soul.
Okay.
But that's acid.
Yes.
Okay.
So now you're going to put on your APIs
Yeah.
and you're going to say, like KA for that thing is 10 to the negative 10. So that's going to buffer at about pH 10. So that's going to be a good way to buffer. So now you have a better tool to solve that problem than you would if you were just taking it. Yes.
So could you repeat that again?
Okay. So the pH
Yeah.
of the buffer
Yeah.
is equal to the pKa approximately. Yes. Yes. So Ka of NH4
Yeah.
is something times 10 to the negative 10. So it's going to buffer somewhere near pH 10.
Yeah.
Yes. So that's going to be your basic buffer. Whereas this one is 10 to the negative 5.
Mm.
Okay, that one is like iron and chokes. Right? No, I'm going to
Yeah.
Yeah.
Oh, okay.
Yeah?
Yeah.
Yeah.
So many years.
Is that how long the screen was?
Well, 4 years was when I was in grade 9, so that's when I started like learning actual stuff about chemistry, right? Chemical formulas. How many years of chemistry? 12? 35? 7? Yeah. So that's why it looks like when I'm like, oh yeah, then you just do this. They're all like, what? Slow down.
Again? What is this? Related on as a week, bro. And it works.
Really? That's awesome. That's awesome.
There's all my cousins like not good business. It's 2 years.
And what comes to you when you think that?
Like, well, you remember I failed that. I feel like you failed stats.
Yes.
I'd be like, you failed stats. What else is it? I am failing stats. My average probably dropped like back like 5%.
Yeah.
Always.
Yeah.
Myself again.
There used to be a game called Trivial Pursuit. Back in the days. It's still around, but it was really big. And a lot of the times,
It's like,
but it was almost like names you only make X. Like, right? So it would be like, which American picture was blah, 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 blah. And I'd be like, Satchel Paige. So I'm like, I didn't use a picture or anything with her. But I'd be like, Satchel Paige, it would be right. Yeah.
wait, that's how we have report this.
Because I can do Oh, yeah.
I was ranking first and second.
Yeah, honestly, yeah.
It works so nicely.
I'm not.
And you can tell by saying, oh yeah, I already knew.
Yeah.
Yes.
Hi, Edward.
Oh.
How you doing? I'm good. Good. I have a quiz to get back to you.
What you're gonna do now before I forget?
It's okay. Over under 50.
Over.
Wait.
Over. Okay.
One, two places to give you.
Oh, two of them.
Two, there you go.
Okay. All right, come. Open sesame.
But then have a question to that.
How long? The other one's like a little bit before. Overnight. All right.